Dr. Eric Bogatin received his BS in physics from MIT and MS and PhD in physics from the University of Arizona in Tucson. He has held senior engineering and management positions at Bell Labs, Raychem, and Sun Microsystems, Ansoft, and Interconnect Devices. He has written 7 technical books in the field and 2 science fiction novels, and presented classes and lectures on signal integrity worldwide. Eric Bogatin is currently a signal integrity evangelist. I've never heard that title before, but I like it. With Teledyne LaCroix and the Dean of the Teledyne LaCroix Signal Integrity Academy at a very long URL that I'm sure he would be happy to provide to you if you ask him, send him an email. Unless you actually want me to read this character by character, but you're good to go now, so I don't have to. Additionally, he is an adjunct professor at the University of Colorado Boulder in the ECEE department and technical editor of the Signal Integrity Journal. So, without further ado, Dr. Eric Bogatin.
Great, thank you.
I'm going to kind of continue the theme that Bruce has set for us to look at why capacitance and inductance is important, in particular looking at the issue of crosstalk. A lot of what I'm going to talk about is in my textbook. 3rd edition is out recently. It's also covered in some of the lectures we have on the Signal Integrity Academy, and also mentioned I'm the technical editor for the Signal Integrity Journal, where we publish a lot of articles about these kinds of using these kinds of essential principles to solve real signal integrity, power integrity, and EMI problems. So how many of you have visited the Signal Integrity Journal? Only a couple of you. Well, if you haven't, I invite you. It's all free. It's all online. We do a bunch of technical articles. You can sign up for the newsletter, and then you'll get a push notification of the table of contents every couple weeks, and you can click on the articles. It's peer-reviewed, and we try to pick articles across this wide spectrum of signal integrity, power integrity, and EMI. Okay. I'm going to give you a little bit of perspective about crosstalk, and we're looking at 2 different regimes. The first regime is when the return path for the signals is continuous, and we'll see there's a particular signature for the crosstalk in that environment. And then we're going to look at the case, well, what if the return path is not continuous? What if it's not a wide plane? And we'll see that the crosstalk dramatically increases. And we'll look at those details. Now, part of this presentation today is not just what is crosstalk and what's the problem, but it's also, okay, what are the mitigation strategies? How do you try to minimize crosstalk? And in order to fix a problem, what's the most important thing you need to know about the problem? Anybody? Not a trick question. Any guesses? What do you need? If your car won't start in the morning, you want to get going, what do you need to know in order to fix that problem? The root cause, exactly right. And I think that is, it's an obvious thing, but it is one of the most important principles in engineering. That is, if you have a problem and you want to fix it or avoid it, you have to know what the root cause is. And to emphasize that, I've got a little cartoon here. These are 2 cavemen. They're watching the pterodactyls fly over here. And this guy's saying to this guy, says, "Are you sure about this, Stan? It seems odd that a pointy head and a long beak is what makes them fly." If you have the wrong root cause for a problem, your chance of fixing that problem is based on pure luck. And that's why it is so important to understand the problem, understand the essential principles behind that problem, and that combination gives you insight into what the root cause is. And if you have the root cause, you use the root cause to solve the problem. So that's the plan of attack. We're going to look at what the problem is we're trying to solve, some of the principles behind it, understand the root cause, and based on the root cause, the solutions will sometimes be obvious. Well, in particular, we're going to look at the problem that interconnects create. If you have a schematic for your design, that schematic tells you about what are the parts you're going to use, the bill of materials. It tells you how things are connected together. But it connects in the schematic with ideal wires. We assume that the wires have 0 time delay, 0 impedance, 0 resistance. They are ideal wires. It tells you nothing about signal integrity, power integrity, or EMI. And when you translate the schematic into the layout, the physical design of those interconnects now start to influence those 3 areas. And so if all you have is the schematic to base your design on, you have absolutely no idea how to design the physical interconnects to avoid the signal, power, and EMI kinds of problems. And so for that reason, I often say that in a schematic, these problems that we're all here to deal with about signal integrity, power integrity, EMI, these problems, they live in the white space of the schematic. They live in those ideal wires and the white space that does the connections in the schematic. It's how the physical design of those ideal interconnects affect the real performance that we care about. And that's what we're going to look at this morning. And so I'm going to identify two kinds of problems, generic problems. They're based on how many different signal paths are involved. When we have one signal path, the signal going down that interconnect can screw itself up. And we call that self-aggression noise. In the case of signal propagating down a transmission line, one way that interconnect can screw up the signal propagating on that interconnect, or in other words, the signal as it propagates can screw itself up, is if it encounters any changes in that instantaneous impedance. Because if the impedance the signal sees changes, what happens? Okay, so I'll give you a little hint. If I ask a trick question, I'm going to go wink, wink, nudge, nudge. Otherwise, they're really as simple as they sound. So, signal is propagating down an interconnect, it encounters a change in the instantaneous impedance. What's it going to do? Reflect, exactly right. And it's those bounces back and forth between the different disconnects, like at the end and the beginning of the line, that causes the distortion of the signal. We call that a self-aggression noise because it's the impact of the signal creating noise on itself. And ultimately, that's what influences or limits the bandwidth of an interconnect. Is one of the contributions is the role of the reflections. Well, today we're going to be talking about not when one signal interferes with itself, but when one signal and signal return path, when that signal interferes with another signal path. And we call that mutual aggression or crosstalk. And we're going to look at these two different regimes where we've engineered the return path to be a nice wide plane, and then when it's not. And we will see the number one, first most important design rule in order to minimize crosstalk is make the return paths wide planes, because if you don't, you will dramatically increase crosstalk. And so we're going to look at this first regime. Okay, we've done that. We've made a nice wide uniform plane. Now, in that regime, the crosstalk's already at a minimum compared to screwed up return path. How do we minimize crosstalk even further? And that's about understanding the mechanism. And Bruce alluded to the answer to this. He said that the real world is really about electric and magnetic fields. We approximate that real world in terms of inductance and capacitance. But if you really want to understand how the world works, it's based on electromagnetics, electric and magnetic fields. So in that perspective, let's look at where crosstalk comes from. And I have two examples here. In the first case, we're looking at, and I just drew these because they're easy to draw, but I've got a couple of microstrip traces. One is the aggressor, one is the victim. And I've drawn, put a signal on there, and now I've drawn kind of exaggerated, the electric fields between the signal and return path of the aggressor and the rings of magnetic fields from the signal return path of the aggressor. And you can see that some of those electric fields, some of them couple over to the quiet line, or the victim line. It is those, we call those the fringe fields. It's the fringe fields, fringe electric, fringe magnetic field lines from the aggressor on the victim line that causes crosstalk. How do you get current through an electric field? What does it take to get current? First of all, when we have a change, okay, well, I'll give you the punchline away. When we have a changing electric field, one of the real innovations that James Clerk Maxwell brought to electromagnetics. He grabbed a Poisson's equation, he grabbed Ampere's equation, grabbed Gauss's equation. He grabbed a number of these, but he added a few really important fundamental additions to come up with the four general equations we call Maxwell's equations. And one of them was this concept of displacement current. We're used to thinking about current as a real conduction current, the flow of some charge. One of the innovations that Maxwell brought along is the idea that in order to unify these ideas of electromagnetics, we need to assume that a changing electric field is just as much a current as a conduction current. And he called that changing electric field, he called it displacement current. So whenever you see an electric field between two conductors, there's no current flowing through the electric field unless the electric field changes. And so if you look at the fringe electric fields between the aggressor and the victim, there are some fringe field lines between them. If those field lines change, there will be a displacement current. That is a crosstalk current from the aggressor to the victim. And so that says the amount of fringe fields is a direct measure of how much potential crosstalk there is. So here's electric field coupling, here's magnetic field coupling. And same thing, you put some signal return path in here, you get magnetic field lines. Some of those that go around the victim line, when do you get induced current from magnetic field lines? What do you need in order to get induced current from magnetic field lines? You need a changing magnetic field lines. And so once again, we see that it's not the magnetic field lines per se that gives crosstalk, it's when they change that we get the crosstalk, when we have a changing signal in the aggressor. But the number of fringe field lines that are around the victim line is a direct measure of how much crosstalk we might expect to see. And so looking at the field distribution gives you a hint at the two most important design features to reduce crosstalk. Because our goal is to reduce the fringe electric and the fringe magnetic fields from the aggressor to the victim. What is one obvious design feature you can implement in order to reduce the fringe fields that go from the aggressor to the victim? The distance, of course. You pull them farther apart, and now you're going to have fewer fringe fields. But remember, it's about the fringe fields. You always have the field lines, both electric and magnetic field lines, between the signal and the return path, but it's because of their extent that gives rise to the coupling to a victim line. In addition to pulling them farther apart, what else do you think you could do in order to sculpt those field lines to keep them confined between the signal and the return path so they don't spread out much?
Put something equal and opposite.
Hold that thought. There's even a more fundamental thing we can do. Very good, exactly right. We want to bring the return path closer. Because if we bring the return path closer, we will sculpt those field lines so they are more likely to go between the signal and return and less fringe field lines. If we pull the lines farther apart, what do you think we do to the characteristic impedance of either of the two lines? Just pull them apart. What happens? Nothing, exactly. Stays the same. But, of course, what's the downside of pulling them? What else do you lose when you pull them farther apart? The real estate, of course, and that translates into cost. And so is Bruce still here? There's one of the lines that he uses that I love to quote him on all the time. He says, engineering is geek for trade-off design. Because ultimately, we're always playing the whack-a-mole game when we do electrical design. That what we do for one feature, to improve one feature, we whack that mole down. When we whack down, another mole pops up. You know the whack-a-mole game that kids' arcades? You whack one mole down, another one pops up. And your goal is you want to whack them down kind of simultaneously to minimize the screwed up problems that they create. And so it's constant trade-off. If you pull the traces far apart in order to reduce the crosstalk, that's great. You've knocked down that mole, but now you've increased the cost because you don't have as much interconnect density. But if you can handle traces far apart, no problem. But if you want high interconnect density, you got to find where is that minimum spacing that you need to hit to balance crosstalk and the interconnect density. Well, that's one effect. Second effect is bring the return closer to the signal line. What's going to happen if we bring so here we are farther apart, here we are bringing the return closer to the signal line. What happens to the characteristic impedance of either line when we bring the return closer? It's reduced. That's the other mole that pops up. Make the dielectric thickness thinner, and now I've got another problem. The impedance is off. And that says that if you live for low crosstalk, you want to work at as low a characteristic impedance as you can tolerate in your design. That's pushing the limits to what you can do to reduce crosstalk. Okay, so these are the obvious things that we can do to reduce crosstalk. Move the traces farther apart. So here I pull them closer. Here's near end, here's far end. And then you bring the return plane closer, and that does it as well. Well, here's the problem. You know, I said that the real world is based on electric and magnetic fields. We approximate those electric magnetic fields. Sometimes it's really hard to solve problems having to start with Maxwell's equations. That's the way the real world is, but if I want to get to the solution in a reasonable amount of time, it's really hard to use Maxwell's equations to solve problems. And so we approximate Maxwell's equations by circuit elements. What's the circuit element that we use to approximate an electric field or electric field coupling? A capacitor. And what circuit element do we use to approximate magnetic field coupling? An inductor. And so we can take that coupling, the electric magnetic field coupling between an aggressor and a victim line, and we can approximate it in terms of capacitive and inductive coupling as an approximation. And it will help us because we generally, and after Bruce's presentation, you have a better feel for the physical connection between geometry and loop inductance and capacitance and geometry, because we generally have a little bit better physical feel for how geometry affects capacitance and inductance. Sometimes it'll get us to the answer faster. And so let's take a look at crosstalk in terms of capacitive inductive coupling. Remember, it's the fringe fields, but we approximate them by capacitive inductive coupling. So I've drawn two transmission lines here. I drew them as microstrip because they're easy to draw, and it points out the important features. The most important quality for this transmission line is that I have a nice wide return path underneath. I'm going to launch the signal down the aggressor, and now as that signal moves by, it's going to encounter some capacitive coupling, the fringe electric field, and some mutual inductance, fringe magnetic field, from the aggressor to the victim. If I have a capacitor, what is the only way you get current through a capacitor? I kind of alluded to it when I talked about changing electric field. That's a displacement current. So what do you need across a capacitor in order to get current through it? A changing voltage. And in order to get noise induced from an aggressor inductor to a victim inductor through the mutual inductance, in order to get that induced current in the victim inductor, what do you need to have happen in the aggressor? A changing current. So the coupling capacitance and coupling mutual inductance, they're geometry features. It doesn't matter what kind of signals there, it's just about geometry. But now here's this edge moving down the aggressor line. At any instant of time, where is the only place you have a changing voltage or a changing current that will give you induced noise in the quiet line? Where's the only place on the aggressor at any instant of time? It's where the edge is. And so crosstalk, as most of signal integrity is very dynamic. It is fundamentally based on the propagation of the signal on the aggressor. So as this edge moves by at any instant of time, this is the only place in which we have coupling between the aggressor and the victim. And what is it that determines the amount of coupled current, capacitively coupled current from the aggressor to the victim? It's the coupling capacitance in that region and the dV/dt. At the same time, we also have a victim loop inductor here and an aggressor loop inductor here, mutual inductance between them. The amount of induced current or voltage signal in the victim from the aggressor through the mutual inductor is all about the di/dt. And so it's the dV/dt and the di/dt of the signal in the aggressor that drives the crosstalk. Well, let's look at the capacitive coupling. We're going to look at both of them. So we've got the edge go by, it sees this capacitance, we get a dV/dt, we get a little bit of current moving over to the victim line. That current into the capacitance of the victim line now generates a little voltage. What is that voltage that is now that noise voltage that's coupled over? What is that noise voltage going to do as soon as it gets into the victim line? Propagate, exactly right. Now comes the trick question. Wink, wink, nudge, nudge. Okay, I've just gotten a little bit of noise coupled into the quiet line over here, capacity coupled noise. What direction is it going to propagate? In the forward direction, in the backward direction? Let's take a vote. How many say backward direction? How many say forward direction? How many say both? Of course it's going to do both, right? And so we're going to get a little bit of noise that propagates in the backward direction, a little bit of capacity coupled noise in the forward direction. And then the edge is going to move along and we're going to get more that's going to go back in one direction, the other direction. Now, it's really hard to visualize that. And so one of my buddies I work at Teledyne LaCroix, and one of my buddies there is the application engineering manager over in Japan, and he has a whiz at writing flash animation code. And when I talked to him about this problem and I showed him these examples, he went back and the next day he wrote this flash animation to illustrate the generation of the capacity coupled current and what it does. And that's available for you. Let me see, I think I have it on the next slide. Here it is. And so if you go to the Academy, BeTheSignal.com, just remember this number. It's VRPW, it's Video Recordings and Presentations and Webinars 3012. You go to the search bar there. This is in the handout, so you can find it there as well. And you can download this little flash animation code. So let me show you that code. And so here it is. And here's what we got. We have an aggressor, we have a victim line, and I have a coupled region. This is where we get the capacitive and later the inductively coupled noise. And I'm going to send a signal down this end, and we're going to look at that edge as it passes by the coupled region. When it passes by there, we're going to get that little burst of current into the victim line that's going to generate a voltage, and that voltage, a little positive current, positive voltage, is going to propagate in both directions. So here's what it looks like. So here's the edge coming by, here's the coupled region, we get capacity coupled current, and we get a little burst of voltage moving back and moving forward. But you notice, let me see if I can do it again here. You notice, look, the edge is moving forward at the same time the capacity coupled noise is moving forward, right? They're coincident, they're moving in the same speed, the same kind of transmission line environment. Suppose we increase the coupled region. That edge is now going to couple in from here, going back from here, from here, from here, and watch what happens to the pattern those little bits of capacitively coupled current do. Here they are, they're dribbling back, dribbling back, dribbling back, dribbling back, they're spreading out, and they overlap, and you get a constant amount of voltage going back. In the forward direction, what's happening? They're building up, and they're getting bigger and bigger and bigger because they're moving forward at the same rate. They're snowballing. They're increasing as the signal propagates. Very different signature for the noise, the crosstalk in the victim that propagates back to the source versus in the forward direction. And so to distinguish those two directions, we call the backward direction, or the near end, near from the source, and the other direction is the forward direction, or the far end, far from the source. So I'm going to make it even more extreme here. I'm going to increase the coupled region even more. And now when we look at the capacity coupled current, we see that we get that dribbling back, giving us a constant amount that we see at the near end, and they all snowball as it moves to the far end. The longer the coupling region, the more opportunity we have for coupling over, the larger the crosstalk. You can see the different signatures at the near end and the far end. Increase the coupled length. What happened to the magnitude of the near end crosstalk over here? Nothing. It just lasts for a longer amount of time. Increase the coupled length. What happens to the far end noise, capacity coupled far noise? It got bigger. Very different signature. Okay, but this is only half the problem. This is only looking at the capacitively coupled current. Now the inductively coupled current. And here's where, thinking about inductance is, Bruce gave us a good start, and I want to add one other piece to it, because he talked mostly about kind of a self-inductance, but it's the mutual inductance that plays a role in crosstalk. And so here we've got the two cases. We've got the aggressor line, that's a signal return loop is propagating forward. That's one loop. And now we have the induced loop in the quiet line that is going to be a signal return loop. When we have a DI/dt increasing in one direction, in this case here, let's increase the DI/dt in the clockwise direction, we're going to get a voltage induced in the quiet line, and that voltage, because it sees an impedance of that transmission line environment, that voltage is going to induce a current. What is the direction of the current loop induced in the quiet line? If we have a clockwise signal return, I guess it's this way. A clockwise signal return in the aggressor, what direction are we going to get as the induced current in the victim line? Is it going to circulate also in the clockwise direction or in the counterclockwise direction? Everybody's saying yes, the counterclockwise. That's Lenz's law. It says the direction of the induced current is opposite the direction of the inducing current in order to minimize the total amount of fields that are generated. So if I have a aggressor current that is increasing in the clockwise direction, the direction of induced circulation of the current is going to be in the counterclockwise direction in the victim line. That's the first key principle about the inductively coupled noise. And here's why it is important. Because now I'm going to go back to our little example here. Here is the aggressor increasing in the signal return in the clockwise direction. What's the direction of the induced current in the victim line? The counterclockwise is going to be going in this direction, circulating in this direction. Now comes the trick question. Wink, wink, nudge, nudge. Here I've just induced this counterclockwise circulating noise, inductively coupled current in the victim line. What direction is that going to propagate? Is it going to propagate toward the source or toward the far end? Near end or far end? Which way is it going to propagate? Huh? Far end. It's going to propagate to the far end. Any others? How many say far end? It's going to propagate to the far end. How many say propagate to the near end? How many say both? It's going to propagate in both directions. And here's the screwy thing about inductively coupled noise, which I think is very counterintuitive. That's where you have to go back and think about Maxwell's equations and also this idea of Lenz's law, the direction of circulation. So I've just said that we're going to get, here we have a DI/dt going in this direction in the aggressor. The direction of circulation in the victim line is counterclockwise. And we're going to get some that propagates in the backward direction. What's that look like? It's circulating this way, propagating this way. It's going to be signal return, signal return, signal return. What's the sign of that voltage that's propagating to the near end? If it's a signal return propagating in some direction, what's the sign of that voltage? It's positive. Now we go in the forward direction. Here's the direction of circulation, and there's going to be some that propagates in the backward direction. So it's going to be going return signal, return signal, return signal, returns. The voltage noise that propagates in the forward direction, what's the sign of that? Negative. And so we have the combination of the capacity coupled current in the backward direction and the forward direction, and the inductively coupled current in the forward and the backward direction. In the backward direction, both of them are positive, but in the forward direction, the capacity coupled current is positive, but the inductively coupled current is negative. Let's take a look at that in Yoshi's simulation. So here is the simulation. We were looking at capacity coupled current before. I'm going to make this only one guy that couples. And now we'll look at the inductively coupled noise. So remember, here's that edge going by. We're going to see a little positive voltage going in the back direction, a little negative in the forward direction, because in the forward direction it's circulating return signal, return signal, return signal. That's a negative voltage propagating in the backward direction as signal, return, just like capacity coupled current. And so likewise, if I increase the coupled region, the signature is going to look the same. It's going to be dribbling back at the near end, building up, snowballing in the far end. So let's do that. Oops. So increase the coupled region, we'll look at the inductively coupled noise. And so we're going to see it each step along the way as that edge reaches the coupled region. It's going to dribble back. We're going to get that signature of a turns on, constant lasts for a round trip time. In the forward direction, we're going to see nothing, nothing, nothing. So it all builds up and we get all that big burst in the negative direction. So in the backward direction, the capacitive inductive current adds. Yeah, question?
What determines the width of the coupling region?
Very good. And so I defined the coupler region by how close they are. So it's like, if you could look at the top view of this, you would see a couple traces far apart, and then they enter a region where they're close together. How close? I'm going to show you in a second, so hold that thought. But it's really how close they are that gives rise to that coupled region. Okay, so let's do that one more time. And so we see the very different signature. The capacitive inductively coupled current in the backward direction are going to add. The capacitive inductively coupled current in the backward direction, they're going to subtract. In strip line, which do you think is more, capacitive or inductive coupling? And again, in an environment where you have a nice wide return path, which is more? How many say capacitive coupling is more? How many say inductive coupling is more? How many say they're both the same? It turns out, in that environment of strip line, where we have nice homogeneous dielectric everywhere, the capacitively coupled current and the inductively coupled current are exactly the same. What do you think is going to happen to the near end crosstalk? Near end. Remember, we saw that the capacitively and the inductively coupled current, they added. They're both the same magnitude. They just add. We get twice the amount of near-end noise from the capacitive and inductively coupled current. But in the forward direction, how much far-end noise are we going to get? None. Because the same amount of capacitive coupled current goes up and the inductively coupled current goes down. So let's look at that case of strip line. So now we looked at the capacitive and inductive separately. Now let's look at the sum of the two. So here's what we're going to see going back in the backward direction. And now you can see the capacitive and inductive, they're the same, they cancel out, and we get nothing in the forward direction. In the case of strip line, where they're both the same magnitude. If we look at the case of microstrip, well, in that environment, the capacitively coupled noise turns out it's less than the inductively coupled noise. Inductively coupled noise is larger. And so what would you expect to see is the sign of the far end crosstalk? If inductively coupled crosstalk is larger, it's going to dominate. We're going to see a negative amount of far end noise. And let's look at that behavior. So here we've seen the coupling. They both dribble back. They dribble back. We're going to get the sum of the two in the near end. And in the far end, because the inductively coupled crosstalk is larger, we see it increasing in the negative direction until it comes out and we get that different signature of far end crosstalk. Okay, very important. And so, okay. So how do we decrease far end, near end crosstalk first? What's the knob to reduce near end crosstalk? Well, we already talked about them. Pull the traces farther apart. And so now the question is, how far apart do we have to pull the traces? Let's take a look at two examples. We said there was a difference in microstrip and strip line because of far end. Now we'll look at near end. So as we pull them apart, the near end cross is going to decrease. The only way to calculate that, you can't do it with pencil and paper, no good approximation. You have to use a 2D field solver. And here is the result of a 2D field solver. Here is the percentage of crosstalk. So here's 1%, 10%. Here's percent versus how far apart the lines are based as a multiple of their line width. This is assuming 50 ohm lines for both of them. One is microstrip, one is strip line. Which one has more near-end crosstalk, microstrip or strip line? Well, it's kind of hard to say here because it depends, right? It depends what the spacing is. If you're really close, separation equal line width, which has more crosstalk, the strip line or microstrip? Surprisingly enough, so in these two, the blue is the strip line and the red is microstrip. That says that at close spacing, strip line has more near-end crosstalk than microstrip. You have to pull them far enough apart in order to decrease the near-end crosstalk. How far apart do you have to go? Well, how much crosstalk is acceptable? Well, unfortunately, what's the most common answer to all signal integrity questions? It depends. Depends on what your spec is. If you're dealing with digital signals, typically 5% is usually acceptable of near-end crosstalk. And at 5% from the worst case, you got aggressor on both sides. that means that between one victim and one aggressor, that's like 2.5%. Well, when you look at where 2.5% is, that's right about coincidentally where the two cross and they have the same amount of crosstalk. And that corresponds to a spacing equal to twice the line width for a 50 ohm environment. That's where that rule of thumb comes in. Hey, how far apart do you want your traces? Roughly twice the line width if you can afford the interconnect density, because then you'll never have a near-end crosstalk issue. What about far-end crosstalk? How do you reduce far-end crosstalk? Well, the same way as spacing, you live at the lowest impedance you can, and then of course, we saw before, it's the length of the coupling. The longer the coupling, the larger the amount of far-end crosstalk. It snowballs. And it also depends on the rise time. So when you put in the numbers with a field solver, we find that the far-end crosstalk scales linearly with length, inversely with rise time. And so the combination of those two, if they scale the same, then it's all about the fringe field between them, and that's about the spacing between the aggressor and the victim line. Okay, and it says that determines how longer you go, the more the far-end crosstalk. If far-end crosstalk's a problem for you, what's the number one way of fixing that problem? If far-end crosstalk, you got to go across the board, you got to have them tightly spaced. You're going to have a short rise time, you're going to have a long distance. Far-end crosstalk in microstrip is going to be a problem for you. How do you fix that problem? Route them in strip line. No far-end crosstalk in strip. Yep, you still got near-end crosstalk, still have to worry about that. Okay, well, I'll skip all that part. And I'll skip all this. So, and we talked about that. So I want to spend the last 6 minutes introducing you to the problem when the return path is not a nice wide return path. Suppose we screwed up that return path. And the kind of problem, the crosstalk that we see, if we screw up the return path, we're going to have capacitive inductive coupling. But the problem is, capacitive coupling, yeah, that's going to increase a little bit if we screw up the return path, but the inductive coupling can increase dramatically, literally orders of magnitude. We call that kind of crosstalk when we've screwed up the return path and we are dominated by inductive coupling, we call that ground bounds. It's a screwed up return, combination of a screwed up return path. What's a screwed up return path? Anything other than a nice wide plane. If we force the return current to take a longer route, and the second criteria is that we have overlapping return currents of the victim and the aggressor line. If we have a screwed up return path, so the signal and return has to do something other than travel in a wide plane under the signal line, and we have overlapping return currents, we're going to see a dramatic increase in the inductive coupling. Here's an example of that. So this is a package. This is a driver. I've got these 5 drivers. 4 of them are switching. The guy down here is pegged low. And so his output is connected to the VSS line. Well, they're leads, or if it's BGA, there's solder balls that go off to the board that connect to the signal lines over here. Here's the return path that also connects onto the board. Once a signal is launched into the transmission line region where they're connected, the signal and return are coupled together. Very little crosstalk in this region, but it's in this region here that I have overlap between the signal return path of the aggressor and the signal return path of the victim. Normally, if this is pegged low, what's the voltage I'm going to see on his output? If he's pegged low, I'm going to see 0, right? Anything above and beyond what I have of 0 is going to be crosstalk. And so I'm going to see inductively coupled crosstalk between this loop, signal return of the victim, and the signal return of the aggressors. And if I have multiple aggressors switching, all of their DIDTs are going to be switching around this loop, and it's where I have coupling to this loop that I'm going to get a voltage noise induced. And this is an example of that measured voltage noise on the victim line when I have multiple aggressors switching. The more DIDT, the more voltage that I get. Here's an example of increase in the number of I/O that are switching, and here's the amount of crosstalk noise in that victim line. And you can see in this example, there's a microcontroller board. I'm getting a half a volt. Half a volt. This is a 3.3 volt system, a half a volt of ground bounce noise in the victim line. The technical term for that situation is you're screwed. And that's why ground bounce can be such an insidious problem because it can be so large. It scales with the number of I/O that switch, that share that same signal return path loop, and it scales with inversely with the rise time. Well, I'm going to skip over a lot of the details here, and I want to just get to the punchline. And again, all this is covered in the textbook, and it's in the notes as well. So what does it take in order to make ground bounce? To have higher mutual inductive coupling between the victim and the aggressor? Two ingredients. One is you want higher impedance in the return path. That means we've screwed up the return path. And the second is overlapping return currents. And so the poor victim line, its signal return path, its loop couples to the aggressor. Where do you have that environment where you don't have a nice wide return? If you have a nice wide return path, we still have crosstalk, near and far and crosstalk. We know how to fix that problem. If you don't have a nice wide return path and you have the overlapping return currents, that's when you're going to have excessive amount of inductive coupling. And in what environment does that happen? Where are the physical interconnects where we don't have a nice wide plane? Here's some examples in packages and connectors. Anything where you don't have a nice wide, if you have an inadvertent gap, if you have via structures, signals going through the vias, the return path has to get from one side to the other through the impedance of the return path. So that's why it's a kind of a misnomer. It's not really ground, it's about return path coupling. And so what's the most important takeaway about minimizing ground bounce? I like to follow the old sage from Ghostbusters. It's about not screwing up the return path and not overlapping the return currents. Don't cross the streams. And Egon says, don't cross the streams. Egon says, why? Egon says, it would be bad. I'm fuzzying the whole good-bad concept. What do you mean, bad? Try to imagine all life as you know it, stopping instantaneously and every molecule in your body exploding at the speed of light. Total protonic reversal. That's bad. Okay, all right. Important safety tip. Don't cross the streams. And with that, I'm going to throw it back up to, so I will mention one other thing. I don't remember if it's tomorrow or on Wednesday. I'm doing some demos in the demo and experiment room. I got 3 of them scheduled. One's going to be on what every scope user needs to know about transmission lines. One's going to be about ground bounce. And I've got this board. I teach a circuit board class at CU. And we build in our class a couple of different boards so the students can see the result of ground bounce noise when you screw up the return path, and then what it looks like when you have a nice wide return path. And we're going to be doing that demo on in the demo room on your schedule, so be sure to check that out. And with that, I'm going to leave you with the last summary. And again, what we've talked about are essential principles, and what you're going to learn the rest of today are essential principles you will use over and over again to kill big problems dead. And so it's the 2 cavemen here, and they just shot this huge mastodon, and one guy's looking at it and says, we should write that spot down. With the principles that you're going to be learning today, you're going to be able to kill big problems dead. And so you want to be sure to write this spot down and the other spots that you're going to learn later today. And with that, maybe I have 30 seconds to answer any other questions anybody may have. I'll be on the floor doing the demos, and otherwise around. Be sure to drop by and say hello. Thank you all very much.